you don't need to, I think you don't need to copy what I am doing, what exactly I want, you need to follow me what it is.
Okay.
So, because if you try to write what I am writing, then you will actually don't have the concentration. Okay?
And is this going to be uploaded then?
I'm trying to record it in the video, so I will give you later on if you need.
Oh, no.
So, this equivalent circuit of induction motor is very, very useful. One of the main reasons of so popular is that the performance of the motor you can actually calculate based on the equivalent circuit. So, first thing is that what are the things we have in the equivalent circuit and how do we actually calculate the performance. So, the equivalent circuit is one phase equivalent circuit. So, it's called per phase equivalent circuit. Even though the motor is three phase, but you can calculate three phase parameters using single phase equivalent circuit. Okay? So, we use the transformer to develop the equivalent circuit. So, the transformer, as you know, the transformer has got two windings. So, primary winding, secondary winding, and they are of course electrically isolated. Exactly the induction motor, if you think of the induction motor is not running. So, you apply three phase supply, it generates three phase rotating magnetic field, and you got the voltage in the secondary. Of course, when this voltage send current, you get the torque, motor rotates. But think of the motor is not rotating. So then it's very similar like transformer. Only exception is the transformer does not have air gap. On the other hand, induction motor has air gap because there is a rotating member. Because of that, you need more current for induction motor to set up the magnetic field. So we use the equivalent circuit of the transformer. So transformer, if you think of that ideal transformer, primary and secondary, but when you have the transformer with real life applications, you need to connect the parameters so that's the transformer equivalent circuit. So here you get the voltage, primary voltage, this is your primary resistance, this is your primary leakage inductance, reactance, this is your core loss resistance, this is your magnetizing reactance, then that comes the ideal. So that's the ideal transformer. And this part you have got the secondary and then you have got the secondary leakage. This is your output of the transformer. So this circuit, when you apply the voltage to the transformer, transformer sends some current in the primary. So you have got the loss in the primary resistance. You have got some leakage field, so the leakage inductance. You have got some core losses, so you take into account with this RC. You need to set up the magnetic field. You take that into account with this magnetizing inductance. That's your ideal transformer. Think of there is no losses. You don't need any current to set up. So your transits are decided by this. And then you have got a secondary, where the secondary resistance and secondary leakage inductance. You connect your load here for supplying the power. So that's the transformer equivalent circuit. We will take exactly the same equivalent circuit for induction motor. Okay? So I can now change the parameters by some name, different name. So the primary in transformer is replaced by stator in induction motor because we give power to the stator. So instead of R1 and X1, we call RX and XS. Okay? So RS stands for, S stands for stator. So RS is the resistance of the stator, XL is the stator reactance. So RS is the now of course this is per phase because we are talking about only one phase. Okay, per phase because we are talking about only one phase. XS is the stator leakage reactance. These two exactly remain the same. Coal loss resistance, magnetizing inductance or reactance. So coming to the secondary side, we instead of R2 or X2, we have RR and XR. So R stands for rotor. Okay, so RR is the rotor resistance, XR is the rotor leakage reactance. Now what is the difference? What is the difference? In case of transformer, we connect the load. Okay, but in case of induction motor, what will happen here? Is the short circuit, because rotor winding, they are short circuited. So this is short circuit. Okay, so rotor is short circuit, rotor is not running, rotor is not rotating. So that's the equivalent circuit of the induction motor. Everyone agree with me? So this is the equivalent circuit of the induction motor when the rotor is not running. Okay, because rotor is short circuited. So rotor is short circuit. Now rotor is not running. So what is the frequency for the rotor circuit? If the rotor is not running, the frequency of the rotor circuit is the same frequency as the stator, isn't it? So it's just like transformer, only exception is more air gap. Now let's say the rotor is running. If the rotor is running now, the frequency of the rotor, not the frequency of the stator. So frequency of the rotor is S of Fs, isn't it? So Fr is the rotor frequency, Fs is the stator frequency. Now rotor is running. So induced voltage in the rotor will be at the frequency of S. So this voltage, if I had ER before, now the voltage will be SER because the induced voltage will be proportional to S. And what will happen to the inductance? So as we know, inductance is omega L, so 2 pi FL. So with the change of frequency, inductance will also change, isn't it? So JSXR instead of XR. So this is at frequency FR, which is SFS. So that's the change of parameter. So here the induced voltage becomes SER and the reactance becomes JXSXR because now it is at frequency which is the slip frequency. What we want to do is that bring these parameters into this side. Okay? Bring the rotor parameters into the stator side. Why we need to do that? Then our equivalent circuit will be much more simple and calculation will be easier. So we have to bring these parameters into this side. In case of transformer, we did that with the help of turns ratio. So if turns ratio N1 into N2, we just converted into the ratio of N1 by N2 whole square. Here we need to do that, but before we do that, we make this frequency as if it is operating at the same frequency. Because if you have inductance in one circuit, they must be operating at the same frequency. Mixture of frequency will not help us. So what we need to do, we need to bring these parameters into frequency of the supply. So how do we do that? So let us say this current is IR. So IR will be SER divided by RR plus JS XR. Okay? So think of that, we divide everybody by S. So we get ER by RR by S plus J XR. So now this equation tells you I have got voltage ER, and that voltage appears when the frequency is exactly the same frequency with the stator. XR is the reactance. It appears as if the frequency is the same frequency like the supply frequency. So what we are doing, we are just changing this parameter as ER, this resistance as RR by S, and this reactance becomes just JXR. So it's just a little bit of manipulation we do there to make the frequency from slip frequency to supply frequency. So now you may have something like N1 and N2, the turns. So if you now change those parameters to this side, what we need to do is multiply those parameters by N1 by N2 whole square. So if we do that, then we can connect them like this. We just make as R dash by S. So R dash, what is R dash? R dash is actually N1 by N2 whole square RR. So that's the referred. So referred parameter to stator side. So we have the rotor resistance. Now the rotor resistance is referred to the stator side. So what we need to do is to multiply by the turns ratio, square of the turns ratio. Similarly, XR dash square is basically N1 by N2 whole square XR. Okay, so we have got the stator resistance, leakage inductance of the stator, we have got the core components, we have got the rotor component, and it is short circuit. But of course, the induction motor is not used just for short circuiting. Induction motor is a motor and it has to do some mechanical work. So it's not that we will waste power in the motor. So motor has to do some work. So this part cannot be short circuited. So in order to make this part short circuited but removed, what we need to do, we just make R dash by S. So RR dash by S as consists of two parts. One part is RR dash, another part is 1 minus S by S RR dash. So if you add them, so it will be S RR dash minus S RR dash, so you get RR dash by S. So what we are doing, we are just again manipulating the component which is RR dash by S equivalent to a resistive component which indicates the loss in the rotor, another component which indicates the power output. So now I will change this. So this one is RR dash, and here I bring so now what it means? So this means this component RR dash This indicates the power loss in the resistance, which we had in the transformer. So transformer had the resistance of the secondary circuit. So that's the component indicates the resistance of the secondary circuit. This component 1 minus S by S R dash, why I have indicated by arrow, this arrow indicates that it's a variable component. Why it's variable? Because of this term S. S is the term slip, isn't it? So as our speed changes, slip also changes. So if you remember what is the definition of slip? Slip is Ns minus Nr by Ns. Ns is the synchronous speed, Nr is the actual rotor speed divided by Ns. So slip is very small and slip can vary from 0 to 1. Because of that we indicate as an arrow. And 1 minus S by S R dash, that indicates the corresponding to power output. Okay, so amount of power output will be is not dissipated, it's the power output in this resistance. That indicates the power output. Okay, so I will draw this circuit again and then explain which component is what. So just to clean up a little bit.
You said don't write anything. Even if I couldn't see you, I would have known that. Even if I couldn't see you or know your voice, I would have known that was you.
Okay, so that's the equivalent circuit we have. So let us see how many parameters you have got. So you have got 6 parameters, isn't it? You have got 6 parameters. One is RS, one is XS, which indicates the stator side. So stator resistance, stator leakage reactance. Okay, RS is the stator resistance, XS is the stator leakage reactance. XM is the magnetizing reactance, which indicates how much current you need for set up the flux. RC is the core loss, which indicates how much is your eddy current and hysteresis loss. R dash and XR dash is the rotor resistance and rotor leakage reactance referred to primary or referred to stator. And this indicates the power output. Okay. So there are two things. One thing is, how do I analyze this circuit? Second thing is, how do I get this circuit? So first I will talk about the analysis and then we will talk about how do we actually measure those parameters. So this is called per phase equivalent circuit. Per phase, because it's the one phase. Ideally, induction motor is 3 phase. So when you do the calculations, you have to take 3 times to take into account of 3 phase. But we analyze for 1 phase. And this is possible based on the fact that the machine is a balanced 3-phase supply, balanced 3-phase system. So if the phases are unbalanced, then of course there will be error. So we assume that it's a balanced supply. So okay, you have this circuit, you are to analyze now. So your current is IS, stator current. So how do you actually analyze this circuit? So first thing is S should be known. S is known. Okay? Why S is known? Because you are analyzing at a certain speed. At certain speed, because you cannot actually analyze. You can analyze with the help of a computer program, and S can be varied. That you can do. But otherwise, you have to calculate on certain running condition. So this is just a alternating current circuits, isn't it? how do you actually make the circuit to find the current? You have to, so this is your series, then it's in parallel, then you can find the equivalent of this, and then add them with this, find the total impedance, and you can find the current. Now, in order to make it a little bit simple, what you can do, you can bring this part, to the front. Okay? So let us say this part, I bring it here. So then my circuit will look like this. Now can you tell me that when can I do that? When can I do that? That type of manipulations, when can I do that? Do you understand what did I do? From this circuit to that circuit, can I do that for every circuit? I cannot do that for every circuit, isn't it? So for example, let us say I have got a circuit like this. So let us say this is my 1 ohm, and this is my 100 ohm, and this is my 50 ohm. Okay? I apply voltage here. And I am telling you that somebody will immediately, I can ask you, okay, can you tell me what is the current in the circuit? Somebody immediately do like this. And get the approximate result very accurately. And correct. So this is the fact that if you think of these two resistance, okay? So this resistance with respect to this is very high. So what will happen? Ideally, if you do not have this resistance, then this is too big. Okay, so let's say this is 90. Okay, it's to 190 because then it will be more realistic. So if I apply 20 volt here, then if you do not have this 50 ohm resistance, what do you expect?
1 amp.
You get 1 volt here, you get 19 volt here, isn't it?
Yes.
So then in this 50 ohm you will get 19 by 50 ampere of current, isn't it? Now you do here, okay, you have got 20 volt. So how much current you will get? 20 by 50 through this, isn't it?
Yeah.
19 by 50, 20 by 50, how much is the error? Is that 5%? So anything below 5%, engineers are very happy. So think of, we are not physicists, we are engineers. Okay? We will be engineers. So anything that below 5%, I ignore.
What if there's like 7 5% in a row though?
So this current, how much you see now, this current changes.
That one will have 1% error, wouldn't
So this current, sorry, it's not 100 ohm now, it's 90 ohm, isn't it?
Yes.
So this current is 1 amp. How much you get this current? It will be 19 by 20 ampere, isn't it?
Yes.
So effectively, you will find that this is possible based on the fact that the impedance offered by the stator impedance is negligibly small. The voltage drop across the stator is negligibly small. So you can actually do this transfer. Now if you do this transfer, it makes our life much more simple. Clear? Because here if you circuit analysis, you have to first find what is the equivalent impedance of these two parallel branch, because this is in parallel with this. But this one, we just ignore this part. This part is taken only for the core losses. We only bother about the torque. We only bother with the power output. So we can just analyze the other part. So many books you will find that we use the equivalent circuit which is given here. But some cases we actually also need to take this way. If they say that you cannot ignore, then we have to take this part, this circuit. Okay? But we will be very happy with this circuit. Clear? So please remember that we do this based on the fact that the voltage drop here is negligibly small. Okay. So now we will calculate the current in this circuit. So what is the current you have? IS. IS is VS. So this is like you have got a alternating current circuit. So you get RS plus R dash by S plus J XS plus XR dash. So what is the total resistance? Total resistance is RS, and R dash plus 1 by S, 1 minus S by S, R dash is give you R dash by S. Isn't it? This part, RS plus R dash by S, the total resistance. Okay? And XS and XR dash is the total reactance. Everybody follow what I am actually trying to do here? I am trying to find the current in the circuit. So if you want to find the magnitude, so this has got two components. It's a complex. It has got two components. One component is the magnitude, one component is the phase. So if I want to do the magnitude, I can write like this. Okay? And of course, you may say you can get the phase angle. Will you follow what I am doing here? So I am trying to get the magnitude and the phase, but most of the time you will find the magnitude, but you may say, what is this phase? Tell me what is this phase?
Sorry, is that minus 10 or?
Minus 10, yeah.
Yeah.
Minus coming because it's in the denominator. That's why it's minus. So what this gives to you? What this gives to you?
The
Power factor.
Power factor. So if I write power factor, so power factor is cos of tan inverse, because that's the angle. So that's my power factor.
Could you theoretically have 3 different power factors if you had different level of inductance in each coil?
What I can.
Well, so if this is one coil and this coil has a power factor built into it because it has an inductance and a resistance, if you built the coil separately, could you have theoretically a combined power factor that has?
No. The coil, any coil will have only one power factor. In this case, the power factor will be different because this is a variable circuit because of the slip. Okay, but otherwise any particular coil you make, the power factor will be constant. Power factor will not change. But this is a change circuit. This is not a constant circuit because of the slip. It's making the circuit variable. So that's the power factor. So in many situations you will be asked to calculate the power factor. So that's the power factor you have. So the power factor is coming from the angle of the current. Okay? Your current is the alternating current. It has got a phase angle. Because of that, you can calculate the power factor. So, now come back to the power consideration. So what is happening? You are applying power to the motor. You are applying power to the motor. So when you apply power to the motor, your aim, of course, to get output power, and you want the output power is as maximum as possible. Ideally, you want all the power you are giving to the input should actually come to output. Ideally. But we live in the real world where idealities need to be trimmed, isn't it? So, once we give the power, we have to provide, first is the core loss, because we set up the magnetic field. So that core loss we have here. So some part of the power goes for the core loss. Second part is the loss in the stator resistance. So stator copper loss. Okay? Second part is the stator copper loss. Once you take these two power losses from the input power, your power then goes here. So this is your air gap, isn't it? This is your air gap. So we call this power is air gap power. What is the meaning of air gap power? The power which actually crossing the air gap. It's like a drain. We are jumping over the drain, or like a river. We are jumping over the river. So it's the power which is actually crossing from stator to the rotor, crossing the air gap. After it crosses the air gap, it has to overcome some of the power in the rotor copper loss. So this is your rotor copper loss. Then the remaining power, you call it power developed. Okay? What is the meaning of power developed? Power developed means this power developed into mechanical form. Because this motor is nothing but electromechanical energy converter. It converts electrical energy to mechanical energy, or electrical power to mechanical power. So this power developed in the form of mechanical. Okay? But as the motor rotates, it has to overcome the air friction. It has to overcome the friction of the bearing. So there are some losses which is called rotational losses. So actually this power which you get as output, you have to take away the rotational losses. So quickly, if I just draw the power diagram, so you will have, just to understand the philosophy. So power input, okay, power input. So first power loss is the
Core loss. Right?
is the core loss. Okay. So core loss. Second power loss is the stator copper loss. Okay. Third power loss is rotor copper loss. Okay.
That's up on a static core. Oh,
Core loss. So core loss is basically you have combination of hysteresis plus eddy. Okay. So that consisting, both of them consisting of the core loss. So then you have got the rotor copper loss. So then you have got so the rest is power out. This power out is actually T times omega is the torque times omega. So you can actually say we can get torque output. So that's the power diagram. It can actually applicable to any kind of rotating machine. Any kind of rotating machines, it will be applicable. Only thing you may say, you have got core loss only in the stator. Why you do not have core loss in the rotor? The reason is the rotor rotates at slip frequency, which is very, very small. And core loss, whether it's the eddy current loss or hysteresis loss, they are proportional to frequency. And that's what you can ignore in the case of induction motor.
So for the core loss, stator loss, and rotor copper loss, there's three essentially resistors that act as the current. Where does frictional and windage loss go? Where do we actually include that in that diagram?
So frictional and windage loss, basically it again, you find that when you have got two rotating members,
Yeah.
your rotating members become hot. So that's the loss converted into heat.
Where does it go in the equivalent circuit?
In the equivalent circuit, you cannot take into account.
So it is.
Yeah, you cannot take into account the equivalent circuit for that. So you have to.
note it outside. The
Yeah, you have to take it as the last part of the.
Why can't you throw it with the load? Because it's a load, it's a load, right?
I mean, you cannot take into equivalent circuit because it's an electrical equivalent circuit,
Yeah.
and you just cannot have anything which represent the core loss as a resistance which comes here, because after that developed power, the equivalent circuit does not give you that part. So the equivalent circuit is how much power is converted into mechanical, that gives you.
Okay, so that's included.
Yeah, you cannot, unfortunately you cannot have that in terms of any resistance. So this is the power flow diagram which you can actually get clear ideas that we have given the input and the losses going out, and then remaining is, and of course we define the efficiency as P out by P in. So now what we want to see is that what will be the air gap power. So okay, first we can say what will be my power input in terms of electrical expression. What will be my power input? So I can calculate the current. Okay, I can calculate the current. I have also got the power factor. So if I ask you now, what is your power input?
The RMS of V and I and power factor.
Yeah. So the power input is Vs, Is, cos of, so let us say this is, so Pf, okay? But this is not a single phase motor, this is a three phase motor. So you have to take three, because you have to include all the three phases, so you have to multiply by 3. So we are analyzing only for one phase, but it's a three phase motor. So you have to multiply by 3. So power in the air gap. What is the power in the air gap? So power in the air gap is this power, isn't it? So you have Pin minus P core minus P copper in stator. Isn't it? So in the core loss, usually you do not have any expression. They will give you how much is the core loss. But if you want to know how much is the stator copper loss, you can actually calculate the stator copper loss, isn't it? So P copper stator, what is the expression if you want to get the expression? So everybody agree with me? So 3I square Rs, because Is is the stator current, I square Rs is the per phase. So stator copper loss will be given by that. So now this one, if I ask you, can you write down the expression of this one in terms of the parameters? P air gap. What can you write? times. So you are talking about RS gone. You are talking about this power. So this power in which circuit? So think of whenever you have any electrical circuit, power is dissipated only in resistance. Inductance, capacitance, they do not dissipate any power. Okay? So if you see from this point towards that, how much is the resistance you have? How much is the resistance you have?
Pressure on S.
R dash by S. Isn't it? R dash by S. Because this resistance and this resistance, if you add them together, that gives you R dash by S. Isn't it? So this and this, you get R dash by S. Because that's what we have written is R dash 1 minus S by S R dash. Okay? So this resistance is actually the rotor resistance representing the rotor copper loss. This resistance is representing the power. So P air gap is this, and P copper rotor. How much is P copper rotor? What is the actual power loss in the rotor resistance? Isn't it? 3I square R at dash. Because that's the rotor resistance which you have got here. Okay? So, what is your P develop? P develop is P air gap minus P copper rotor. Okay? So, that is actually 3 I square R dash by S minus 3 I square R dash. So that gives you 3 I square R dash 1 minus S by S. Okay? So I am just taking away this copper loss in the rotor from the air gap, air gap power.
Where does the power factor go for the PAG, P and P?
Power factor is here.
Yeah, but why does that not appear in PAG?
Or it will appear because it will appear in the current.
Oh,
Okay.
okay.
But we are not power factor. See,
It's
in
only for
any
power.
in any alternating current you have got the magnitude and the phase angle. So power factor is in the phase angle. So this one is 1 minus S PAG. So P develop is actually 1 minus S times PAG. So this P develop, if you think of that, actually we are talking about system where we do not have any frictional windage losses. Then this P develop is nothing but P output, which is torque times omega, isn't it? So P develop I can write as P develop is torque times omega is P develop. So you can say this torque, which is P develop by 1 minus S times omega S.
Well, where does the mechanical losses come in?
I can ignore the mechanical losses, okay, just for the expression, the torque. So what I mean is that what is the torque developed, and then of course the output torque will be slightly less than the actual developed torque. So just I think I'll okay. So I will delete this part and I'll draw again. Ready? So that's my developed power. So what I want now is the developed torque. So I'm interested because in a motor, when you think of any motor, the most important thing of the motor is the torque. Okay, how much torque the motor gives, and the relationship between torque and speed. So how the torque changes with speed. So whenever you select any motor, you have to look into the torque speed characteristics. And different motors, they are suitable for different applications. So for example, you see the train, they are specifically using a particular type of motor. Do you know what is that motor?
The city trains.
The trains and the trams. Okay, trams of course you don't have here in city.
1500 volt DC as far as.
Is the DC series motor. Because what happened when the train runs at the time of starting, it needs huge amount of torque. Because the overcoming the static friction is very, very difficult. Once somebody running, is the kinetic inertia comes into picture, you do not need that much power. So during the starting, you need very high torque, but in running, you do not need so much torque. So you will have a characteristic something like this. Okay? So this is your speed, this is your torque. So you will have very high torque at starting, but then very low amount of torque at running. So that's the series motor suitable for this. So torque speed characteristic, this is called torque speed characteristics. You know as a function of speed, what is a torque. So we are interested to know what is the developed torque. So P developed is the torque developed times omega. Okay? So this omega, what is this omega? This omega is actually 2 pi n by 60, isn't it? 2 pi nr by 60. So I can also write it as 2 pi, this is 1 minus s ns by 60. So this P developed, if I now write it as 1 minus s P air gap, so I can find out what is my developed torque. So T developed is 1 minus s will be cancelled, so P air gap, and you will have 2 pi ns, of course this 60 will come, so you get like this. So if I know what is my P air gap, what is my power developed across the air gap, I can actually also find what is my torque, developed torque. The actual torque will be slightly less because there will be some frictional and windage which here it has to overcome. So first thing is I will try to see here, can I have a torque speed characteristics of the motor using these equations. Okay, so what is my P air gap? If you remember, P air gap is this one, 3I square R actors by S. Okay. So what is your IS? So I will use this one. So remember this one. This is our equation. P air gap is 3I square R actors by S. So I'll draw again quickly the equivalent circuit. I'm drawing because you will find that it's not too difficult. That's why. Okay, it's not too difficult at all. So P air gap is 3 I square R dash by S. So this is your IS. So what is I square? So I square is B square R is R dash by S whole square plus X square. So let us say X equal to XS plus XR dash. So times R dash by. Do you agree with me?